my name is Yuting Wang. Together with my collaborators, I present our work, Active Learning for Weakly-Supervised Object Detection. Real-world images often include many instances of important small objects. For instance, real pizza 10 images contain multiple instances of pepperoni, tomatoes, or other ingredients. Typical object detectors fail to accurately detect and recognize those objects. To train object detectors that can succeed at this task, while balancing the trade-off between detection performance and annotation effort, we consider training on a combination of large weakly and small fully labeled data. Weakly labeled images contain only image-level labels. Fully labeled data contains bounding boxes of individual objects in images. To that end, we developed a new active learning annotation approach, ALWOD, to improve the annotation efficiency while simultaneously increasing the object detection accuracy. We utilize semi-supervised learning that relies on student-teacher object detection networks to select the most informative samples. To balance initial detection performance with annotation cost, we pre-train the object detector on a large fully labeled auxiliary domain constructed from an initial set of the few fully labeled images. To construct the auxiliary domain, we combine real-world background images with real foreground objects that are pasted in a realistic manner. The foreground objects are cropped from the fully annotated images, which are randomly selected from the weakly annotated set. By doing this, we can create a large fully annotated auxiliary set that has the same annotation cost as a randomly selected image set. The main challenge of active learning for object detection is defining an acquisition function alpha. And each active learning cycle T, the student-teacher network MT, learns from the dataset ST, including the weakly labeled set with indices WT and the fully labeled set with indices FT. After that, an acquisition function alpha will select a set of the B weakly annotated images with indices AT plus 1, which will be passed on to a human annotator to label. After the annotation process is complete, the student-teacher network is fine-tuned on the updated target images ST plus 1. The fine-tuning process continues until the annotation budget is exhausted. To select informative training samples, we consider two acquisition signals: the disagreement between the student-teacher network pair and the uncertainty of the teacher network's predictions. In an ideal case, the student network's predictions would be consistent with the teacher's prediction. This naturally leads to using the discrepancy between student-teacher networks as one of the acquisition signals. We then fuse these two signals to arrive at the final acquisition function. Empirically, we find that taking the product of the two acquisition scores performs better than taking the sum. In our approach, all images from the most recent active learning cycle are presented to the annotator in an ordered list according to their acquisition scores. Each image contains many predicted bounding boxes with class labels generated by both student and teacher networks. The annotator is asked to select the positive bounding boxes from proposals that overlap with true objects and include at least one of the four extreme points: top, bottom, leftmost, and rightmost. Correct the bounding box categories if they are incorrect, and assess the quality of bounding box. Any unselected bounding boxes are removed. By using acquisition scores to prioritize the annotation of images, our tools allow annotators to label objects more efficiently and accurately. On average, our annotation process can be completed in only 2 seconds, while the traditional annotation process can be completed in 36 seconds. We compare our method with state-of-the-art WSOD, SSOD, and ALWOD baselines. The results demonstrate that our method ALWOD outperforms all the baselines, generalized across different datasets, and generalized to different detectors. We observe that our method not only locates the most objects, but also produces more accurate bounding boxes and more correct class labels compared with other baselines. For all technical details and results, please see our poster 1985. Thanks.